so far. What you know about city in terms of theory of city? Anyone? Yes? Yes. And this is what we memorize. Right. You see, I am giving you definition. There is no pointer also?
Yes. Pointer is there.
Yes, which one? This one, okay. And slide changer is also there? No, okay. You see, circular dichroism by definition I have written here. And entire almost over 1 hour lecture I will be talking about it. The linear polarized radiation corresponding to superposition of left and right circular polarized waves. In optically active medium, these two components are absorbed differently, and this phenomena is called circular dichroism. What I am saying that a linear polarized radiation that is originated from superposition of left and right circular polarized radiation, left and right handed circular polarized radiation. If such linear polarized radiation passes through optical active medium, and when out of these two components one is absorbed more or less, this phenomena is called circular dichroism. Right? Now I will explain you all these things a little bit in detail. How linear polarized radiation is generated using a left and right handed circular polarized light. And when this linear polarized radiation passes through optical active medium, what happens is if one is absorbed more or less. Right? So let's have little discussion about what is, sorry, oh, this is no slide. So let's have, yes, it's what that.
सर मेनू प्रेस कर दीजिए सर मेनू.
Okay. So let's have little talk about electromagnetic radiation. What you know about electromagnetic radiation? Anyone? Anyone? You see, electromagnetic radiation is, here what I have written. Electromagnetic waves are periodic change of electric and magnetic field in space. So you can see here, electric and magnetic field are changing in space and time. So you can see electric and magnetic waves. These waves are perpendicular to each other. And direction of light is perpendicular to each of these two. So you see electric field, magnetic field and direction of light, right? See, you see electric field is always perpendicular to magnetic field and direction of light is always perpendicular to these two, right? You see, for simplicity, from next slide, I am showing only electric field. But when I show you electric field, you always have to imagine that you also always have a magnetic field perpendicular to this electric field direction. Right? Now, what is polarized light and what is unpolarized light? Anyone? What is polarized light? You see, at any point of time, you have light passing in this direction, this direction, this direction, this direction. Right? So I am showing you in the next slide. You see, at any point of time, you have magnetic field in all possible directions. And in all these directions, you always have a perpendicular electric field and also direction of light perpendicular to all of these. So I would say you have a random orientation of light. So what all lights you are seeing is unpolarized, right? You have random orientation of light. This you don't fan because I have taken time. I had little headache. I have taken some paracetamol, so that's why I'm having little sweating. So rather I would say light is random, right? So when we pass this random light through this polarizer, it selects light in one direction. This is called plane polarized light, right? So what we have discussed so far, I will just review before we go in complicated things. We have discussed that in light we have electric field, we have a magnetic field, and perpendicular to these two we have direction of light. Right? At any point of time we have light in all directions. Right? So we have magnetic field, electric field, you can see in all these directions, and perpendicular to all of these we have a magnetic field and light passing in all directions. Right? Now when we pass this light through polarizer, we have different type of polarizer, then you have a light that is passing in a given orientation, that is called polarized light. So in subsequent slides, I am making two changes. One, I am showing you only electric field for simplicity, because we will be talking about so many different types of light that it will make it more complicated. So I will show you only electric field, right? So when I show you electric field, you just imagine that you also have a magnetic field, right? Now let's see what I am showing in next slide here and what you make out of this. What is this? You are seeing here the wave of electric field. And if you are seeing at this point, you are seeing that with time, this electric field is oscillating in a given direction. I am showing you only electric field, but you just imagine that there is a magnetic field also. Right? I am just showing it to make things simpler because it will become little more complicated in coming slides. Now you can see this electric field oscillates in vertical plane, and this is polarized light. Right? I am talking about polarized light. Now you have used a polarizer. You just, if you are getting confused, you just go to our previous one. So I am talking about this light. I am talking about this light. Right? So you can see what you are seeing. The electric field is oscillating in vertical direction. We call it vertical polarized light. Right? Very simple. It's polarized light in a vertical direction. I am showing only electric field, not to get confused. And this one, again very simple. What is this? No. Horizontal polarized light. You see, the earlier one was vertical polarized light, this one was horizontal polarized. And superposition of waves. How two waves meet? I will talk about how waves meet in next slide. Waves meet. What happens when waves meet? What is superposition of waves? Anyone? You see, what I am trying to explain, that at given point of time, let's say if a vertical polarized light and horizontal polarized light meets in the same phase. When I say same phase means, I am telling you two things. Vertical polarized light and horizontal polarized light with same intensity meets in the same phase. When I say lights meeting in, waves meeting in same phase, what does it mean? Anyone? when they meet in same phase, means they reach peak and dip at the same time. When one reaches the peak, the other wave is also reaching peak. When this reaches zero, other is also reaching zero. And when this reaches dip, other is also reaching dip. Right? So when horizontal and vertical polarized light of same intensity gets superimposed with same phase, what is resultant? Resultant is again a plane polarized light at a different angle, 45 degree of this. So, you know, if you have a vector here, if you have a vector here, let's say this is vector A, this is vector B, you all know resultant is? Right? So you can see here, I wish this was little slow. You can see both, when both reaches zero, resultant is also zero. When both reaches negative, right, resultant is A plus B negative. So you can see the resultant is also a plane polarized light, but in different plane. Now I am asking you to imagine, I will not go to next slide. If they meet with a phase difference of, let's say 90 degrees, what will happen? I am telling you that let's say when one vector is at peak, other is zero. 90 degree difference means what will be the resultant? Anyone? What will be the resultant?
A plus B plus B.
If I show you next slide, you will immediately understand, but I am just asking you to do some exercise. You see, when these two vectors meets with 90 degree difference, what is resultant? You can see here, when one is at peak, other is zero. This has, let's say this was 10, right? Now in next stage this has become, let's say this has become 8, this has become 2. Resultant is 10. This has become 7, this has become 3. Resultant is still 10. So you can see it will be circular polarized. But if they meet minus 90 degree, means the one that was peak, in this case, let's say when red one is at peak, the other one is 0. Now if opposite, one is at peak, the other is 0. What will be? Here also circular polarized light, but direction is changed. If you are okay, then only we will move ahead. If you are able to see this, here, I am showing you these two features. Now, you have learned how these two left and right-handed circular polarized lights are generated. Right? Anyone has doubt? What we have learned? We have learned how left-handed and right-handed circular polarized light is generated. But we don't use this light in CD. I have said that plane polarized light originated from superposition of this left and right-handed circular polarized light. Means from these two lights we generate linear polarized light. and then that light is used in CT. Right? I hope you are clear up to here how left and right-handed circular polarized lights are generated. Now you see, these circular polarized lights are superpositioned. What you are seeing? What is this? I am telling left and right-handed circular polarized lights are superpositioned in same phase. Same phase means when one reaches peak, other also reaches. So you see, resultant becomes sum of those two. One reaches dip, other also reaches dip. Resultant becomes sum of these two. And at zero, both are opposite, so get cancelled. Right? So you see, resultant is linear polarized. So this linear polarized light we use in circular dichromation. Right? So linear polarized light originated from superposition of left-handed and right-handed circular polarized light. Now from here we will start discussing what happens in CT. Right? Let's see, if I pass this light in optically active medium, we will have some more discussion about it. There is another thing I thought I will explain. Let's see. What you are seeing in this one. This is what you generated from superposition of left-handed and right-handed linear polarized light. Now what you are seeing, that one component is more absorbed. You see what is coming here from this, you pass this light from a medium, and what is coming here, one component here, you see this one is more absorbed. Now both left and right-handed are not equal in intensity. Right? When you pass the light in the medium, both were equal in intensity. But when it came out, both components are not equal in intensity, because out of light, left and right-handed, one is absorbed more. What is resultant? Resultant would be elliptical polarized light. Why? Because you can imagine when both were in zero, because of equal intensity they were cancelled. Now since intensities are not equal, they will not be cancelled, it will have some value. Right? This is called circular dichromation. You can see here, this circular polarized light is converted into elliptical polarized light because one component is absorbed more. Before we move ahead, is this clear to everyone? Right? You can see this circular polarized, this linear polarized light originated from superposition of left and right-handed circular polarized light. When passes through an optically active medium and one component is absorbed more, this linear polarized light becomes elliptical polarized light. This phenomena is called circular dichromation. Right? Although this topic is not, we are not talking about optical rotation, but since it's very much related, I will just talk about a little bit, then we'll come back to CT. There is another technique called optical rotation. Or circular birefringence. What is that? Very related topic. Here also, what have you heard about this circular bifurcation or optical rotation? Many city, I don't know if it, one thing you don't have.
Yes.
When many city has both, you can take CD and you can take ORT. So in this model also we have ORT. ORT. Before I explain you ORT, let me ask, what is refractive index? What is refractive index? Anyone?
Some of like when we have photosynthetic light from observer, some of like it's
You see, in layman's language, refractive index is like light वैक्यूम में जिस रेट से ट्रेवल करेगा बाय लाइट उस मीडियम में जिसमें ट्रेवल करेगा सी बाई वी क्या बोलते है ना, उसी को रिफ्रैक्टिव इंडेक्स बोलते हैं. नाउ इफ यू हैव ए मीडियम, listen carefully, if you have a medium where refractive index for left-handed and right-handed, in earlier one was absorbance, in circular dichroism we had different absorbance for left and right-handed. Now if we have a different refractive index for left and right-handed, what will happen? You see, both waves have started in same plane. Right? Both have same type of zero and same time of, but because they differ in refractive index, they will not remain in same plane. One will move faster and another will move slower. What will happen? Their phase will change. Their phase will change after they pass through the medium. What is effect? Now they are meeting at this point. Now they will meet at this point. You can see from here also. At the same phase, they were meeting at this point. Now phase has changed. They will meet at different points. But intensity remains same. The resultant would be again vertical polarized light, but at a different angle. And the change in rotation is called ORD. But ORD is not topic for today's discussion. I thought since it's very related, we'll just stop. Right? Now let's see. Come back to this again to memorize your concept, so you don't go in ORD too much. Here, vertical polarized light converted into elliptical polarized light. Right? This is what is happening. CD, how we explain CD? You see, you weigh 1 kilogram, 5 meters, right? Distance you say 1 kilometer, 1 kilogram weight. How we express CD? Right? Linear polarized light becoming elliptical polarized light. If you have to tell this in terms of quantitative terms, this statement that vertical becomes elliptical is qualitative. But when you have to tell how much CD, you have to define some parameter. Right? So CD we explain in terms of ellipticity. You can see here. We will spend little time on this slide. You see, this is your electric field, right-handed, left-handed, right-handed circular polarized light, left-handed circular polarized light, right? At peak, when they meet at same, you see, when they meet peak at same phase, you add the sum. It becomes sum of these two. Here, if both are not equal, resultant becomes equal, let's say ER minus EF. That's why it becomes elliptical polarized light. And we define this by a value theta. and this is called ellipticity. Ellipticity, right? So CD is defined as ellipticity. Right? And that ellipticity is actually theta. And you all know what is tan theta? You can see this one by this one. Okay. Now I will ask you a question. Let's say if there is no absorbance, I mean if you have equal absorbance of both, what would be tan theta? You see, I said tan theta equals ER EL by ER plus EL. You all agree? Now let's see. I'm asking you two situations. One, let's say one of these, let's say EL, is totally absorbed, 100% absorbed. What would be the resultant? अब उतना सोचने की सोच के बताओ तो अच्छा है, लेकिन नहीं सोच के बताओगे तो वहां से ये टोटली एब्जॉर्ब हो गया, ये टोटली एब्जॉर्ब हो गया, है ना? तो ये जीरो हो गया, ये भी जीरो हो गया, ये दोनों कैंसिल हो गया, 1. tan थीटा अगर 1 है तो क्या हो गया? tan थीटा अगर 1 है तो एंगल क्या होगा?
5/4. 5/4. 45 डिग्री.
45. मतलब 45 डिग्री होने का मतलब ये एंगल 45 होने का मतलब क्या हुआ? जितना ये है उतना ये है, मतलब ये क्या रह गया? सर्कुलर पोलराइज्ड रह गया. अच्छा, ये मान लीजिए एक जो है दोनों बराबर एब्जॉर्ब हुआ तो क्या हुआ? अब थोड़ा यहाँ पे हम लोग थोड़ा सा आगे इसी स्लाइड जो जाते हैं हमने लिया, एक्चुअली हमने क्विकली विकिपीडिया लिया है तुम लोगों को पढ़ाने के लिए, मतलब फॉर दिस लेक्चर. You see here it says when ER/EL, when there is no difference in absorbance of right and left-handed circular diagram, theta is 0. क्यों 0 होगा? भाई अगर दोनों में कोई डिफरेंस नहीं है तो ये ऊपर वाला 0 हो जाएगा. किसी को 0 से डिवाइड करो तो 0 रहेगा. मतलब अगर दोनों में एब्जॉर्बेंस में डिफरेंस नहीं है तो सर्कुलर डाइक्रोइज्म तो हो ही नहीं रहा. क्या हो रहा है फिर? ये थीटा 0 हो जा रहा है, वर्टिकल पोलराइज्ड लाइट जो है वर्टिकल पोलराइज्ड है. एक दूसरा, व्हेन आइदर EL और ER इक्वल्स टू 0, so theta becomes 45. Right, light is circular, remains circular polarized, है ना? थीटा 45. थीटा 45 होने का मतलब क्या हुआ कि ये जो साइज है ये भी वही साइज है ना? अब एक चीज हम लोग बताएंगे, इलेक्ट्रिसिटी. अब ये सब चीजें हम नहीं बात कर रहे हैं, हम डेफिनेशन डेरिवेशन पे नहीं जा रहे क्योंकि बहुत सारे लोग मैथमेटिक्स में उतने कंफर्टेबल नहीं होंगे. बट हम थोड़ा सा लास्ट में I will just explain you how electricity is calculated. What is essentially circular dynamics? अगर हम vertical polarized light becoming electrical polarized light इसको भूल जाए, हम इलेक्ट्रिसिटी को भी भूल जाए. Essentially, what is circular dichroism? Circular dichroism is this. What is this? Difference in molar extinction coefficient for left-handed and right-handed. Right? What is molar extinction coefficient? What is epsilon?
Extent of light absorption. Extent of light absorption.
What is Beer-Lambert's law? ये तो याद करने की बात है. क्या? अगर हम थोड़ा लेमैन्स लैंग्वेज में बोले तो एक्सटिंक्शन कोएफिशिएंट इज absorbance of one molar compound when path length is 1 cm. अब इसी के डिफरेंस को जो है हम बोलते हैं CD. CD is nothing but difference in absorbance for right-handed and left-handed. और ये हम कैलकुलेशन में नहीं जाते, इलेक्ट्रिसिटी फाइनली इज दिस. अब हम लोग थोड़ा बिफोर वी गो इनटू एप्लीकेशन just have a quick review what we have studied so far. कौन इसको 2-3 मिनट में बताना चाहता है? कौन इसको 2-3 मिनट में बताएगा what is CD? Anyone? I will help. बताओ. कोई नहीं यार, ये तो इतना याद हो जाएगा.
सर वो मोनोक्रोमेटिक लाइट को जब प्लेन मल्टीपोलराइज लाइट को जब मोनोक्रोमेटर से पास कराते हैं.
नहीं, मैं केवल ये बोलना चाहता हूँ कि ये डेफिनेशन जो हमने दिया है ये सब लोग समझ गए. अभी तक हमने कितना भी बताया, हमने डेफिनेशन बताने के हमने बताया कि लीनियर पोलराइज्ड रेडिएशन corresponding to superposition of left and right-handed circular polarized light. The linear polarized light that is originated from left and right-handed circular polarized light of same intensity meeting in same plane. In optical active medium, these two components are absorbed differently. This is called circular dichroism. Vertical polarized light become elliptical polarized light. We define CD in terms of ellipticity, है ना? और हमने बताया कि भाई एक पूरा एब्जॉर्ब हो गया, एक नहीं हुआ. Now let's see for what purpose we use CD. Right? I will talk primarily related to proteins. What is optical active medium?
Which can rotate plane to other. It can rotate plane to other.
That can rotate plane of polarized light because it has asymmetric what? Chiral center. This chiral center asymmetry हम लोगों ने क्लास में भी पढ़ा. कार्बन से चारों ओर जुड़ा हुआ जो है वो अलग अलग है. It's optically active. But this asymmetry can be structural also. Now, proteins are primarily peptide bonds are inherently asymmetric. अगर ऐसे भी देखो, यहाँ पे भी अगर देख लो, यहाँ पे भी अगर देखें तो ये देखो ये कार्बन से सब अलग अलग ग्रुप जुड़े हुए हैं, और it has a structural asymmetry also, and that structural asymmetry depends on phi and psi angle. हम लोगों ने पढ़ा है कि भाई प्रोटीन पेप्टाइड बॉन्ड इज रिजिड, इट कैन नॉट रोटेट, भाई ये दोनों है, और प्रोटीन एक्वायर्स इट्स स्ट्रक्चर बाय रोटेशन ऑफ phi and psi. Right? Now, this peptide bond remains stable. It has some asymmetry, but around peptide bond we also have a structural asymmetry. We also have a structural asymmetry. Depending on what is phi and psi angle, we have different characteristic of CD in different proteins. For example, if we see, I will just review quickly, then we go in detail. If we see this, अच्छा एक चीज हम बताना भूल गए. What is negative CD? You see, when we see electricity, you will find that at some point we are seeing electricity positive, at some place we are seeing electricity negative. And पर ये एंगल इस तरफ जो है वो पॉजिटिव है, इस तरफ है तो नेगेटिव है ना. तो इलेक्ट्रिसिटी अब प्रोटीन स्ट्रक्चर have different characteristics of CD. I'm not going too much in chemistry of this, but you see, a random coil gives a characteristic CD spectra. Means if you have different wavelength, right, it will have differential absorption of light at different wavelength that will follow a characteristic pattern, right? Likewise, if you have a beta CD structure, it will follow a characteristic pattern, right? And likewise, alpha helical structure will follow a characteristic pattern, right? And here I have summarized some details. But for what purpose this information is useful? For example, let's say if you have alpha helix, it gives two negative peak at this, one positive peak at this, and so on spectra. But if you collect CD spectra, what information you get? The first, CD spectra doesn't give you precise structural information. It's not a crystallographic or cryo electron microscopy or so on. It gives you very rough detail about the structure. It gives very crude detail. It's beta sheet, alpha helix, how beta sheet is changing, how alpha helix is changing. So many times it's used for quick screening, but you can do lot of different types of studies. Right? Let me explain few things that we can use and do from CD. Let's see. Can you gather anything from this curve? Can you gather anything from this curve? And what you know about protein stability? You all know protein is polymer of amino acids, and it needs to acquire a given structure, three-dimensional structure, before it becomes active. Okay? Let's see if I start denaturing the protein using some denaturing. Let's say here I incubate my protein, let's say 0.25 guanidine hydrochloride and so on at all different concentration. And I have plotted something called fraction unfolded. Right? Let's see what I'm trying to explain, how I make you can stop me if you don't understand. Fraction unfolded, let's say for a alpha helical structure, I am following CDS spectra at 222 nanometers. Right? And a native protein gives you a value of, let's say, minus 12 unit diameter, ignore it. And a denatured one gives you a value of, this is native, and denatured one gives a value of minus 2, this is denatured. Assuming that protein has only two conformations, native and denatured, depending on what elasticity you are getting at different bonding hydrochloride concentration, you can know that what fraction is in native form, what fraction is in denatured form. Right? Native and denatured difference in elasticity is 10. So, if elasticity is, let's say, minus 5, means fraction unfolded is, नहीं समझ रहे हो भाई, हम बोल रहे हैं कि a native protein gives negative elasticity of minus 12. Denatured one gives, let's say, minus 2. Difference between native and denatured is 10, minus 10. Right? So, at any point, at any concentration of denatured, depending on what is elasticity, you will know what fraction is native, what fraction is denatured. Let's say, if elasticity is minus 7.5, what does it mean? Means 75% is native, 25%. So we just, the fraction unfolded means we say, we normalize the data between 0 to 1, saying that what fraction is folded or unfolded. Here there is assumption that protein is either in native or denatured. So we incubate protein at different concentration overnight, collect CD, and we plot fraction unfolded. Right? This, let's say this is one protein, this is other protein. So you can easily see that this protein is more stable compared to this. Here, let's say around 2 molar guanidine hydrochloride is required for 50% fraction unfolded, while here the same 50% unfolding is done at 1.8. But this information looks very primitive, not much detail. Right? Can I tell in terms of qualitative that delta G of this protein is this much and this protein is this much? Right? So this much is free energy difference. For example, if you make a mutation in protein, if you try to engineer a protein, you can quantitatively tell how much energy change has happened upon making the mutation in protein. Right? So let's try to see how we can tell these things in quantitative terms. Right? I will move only if these things are clear to everyone. Right? Did you all understand how I am writing this fraction unfolded? I am just normalizing data. Let's say your 2 minus 2 is denatured, minus 12 is native. You are normalizing the data difference between 0 to 1. Right? So, fraction unfolded 0 means native, fraction unfolded 1 means denatured. unfolded 0 means native, fraction unfolded 1 means genetic. So how I am plotting this data, is this clear to everyone? No? This data tells you in cruder way that using this data you can, in crude way you can do some analysis. Right? Now let's see, you got, in one case, you got a curve like this. Fraction unfolded. You got a curve where you have a situation like this. Means here you have something which is stable to certain concentration. That is used for, that is primarily indicates folding intermediate. You see here you can see you have only native and denatured, but you see if this curve has this curve is coming like this here, then it indicates some folding intermediate. What I am telling is this, that this type of curve gives you some qualitative data, not quantitative data. This tells you if curve is like this, it tells you some intermediate. If this 50% unfolding requires one guanidine hydrochloride, you can tell it's more stable. Now we will see how we can do things in little qualitative way. Let's see here. Before I come to this, let's I'm not about to clean this. What is delta G?
Change in Gibbs field.
Free energy change. Something is going from one state to other state. The free energy change is called delta G. Right? How we define delta G? Let's say in my earlier experiment, just previous slide, I have taken my protein and incubated at different concentration of guanidine hydrochloride. What is happening? Protein is getting incubated at different concentration of guanidine hydrochloride, and then you are seeing the CDS spectrum. Right? How, what, how you derive delta G? What is value of delta G?
So delta H minus T delta S.
Anyone? What is delta? I mean, accordingly I will decide with what depth I have to go. Delta G equals delta G naught plus RT ln K. Okay. I will just go to my previous slide first. Let's say you pick up any concentration. Let's say 1 molar guanidine. You have incubated your protein, you have kept it overnight. Now protein is in equilibrium at 1 molar of guanidine. When I say in equilibrium, what is that? I say if protein is net is 0, is it only native, just native? You see, you listen carefully and you can just stop me if you don't understand. You see, in this case, always there is equilibrium between native to denatured. In 0 molar, equilibrium is shifted towards native, means you have primarily native. If your protein is here, your equilibrium is shifted towards denatured, you are primarily denatured. And all these concentrations you have native and denatured in equilibrium. Right? Now, let's say if I tell at 0 molar of guanidinoate hydrochloride, let's say you have put your protein in buffer. Protein is in equilibrium, right? If something is in equilibrium, what is delta G? If system is in equilibrium, what is delta G? Zero. Huh? Delta G is something that drives you in one state to other. But if it is in equilibrium, there is no drive to move from one state to other. So here, your delta G is 0. Your delta G is 0. What is delta G naught? Delta G naught is called a standard state failure, where you define temperature, you define condition. So here, let's say temperature is 30. Right? So, in equilibrium, this delta G naught is minus RT ln K, where K is equilibrium. K is constant. What is K? K in this case ratio of D by N. Right? Here it's in equilibrium. What I'm trying to tell, in all these concentrations, since protein is in equilibrium, its stability is primarily defined by delta G naught, not delta G, because system is in equilibrium. Delta G is 0, right? So its stability is defined by delta G naught. Now, since at every point of this curve, you know what fraction is in what fraction, let's say here at 2 molar, you know that in 2 molar system is in equilibrium, but ratio of denatured and native is this. At every concentration you can calculate delta G. Is it? So, in this slide, what I have done here is this. At every concentration, I have defined delta G naught, and then we extrapolate it to 0, that becomes stability of native protein. Let's say you have different concentration and you have extrapolated it to 0. Someone may ask, stability is not positive. In nature favors delta G negative. Two questions. Why this is coming positive? Why this is coming positive? Why this one coming positive? You see, delta G naught at lower concentration, delta G naught, let's say minus RT ln D by N. Right? You see, if guanidine hydrochloride concentration is low, denatured fraction is less, native fraction is more, ln value is less than 1. If log is less than 1, it's negative. Negative becomes positive. Right? But what does it mean? This positive means that if you convert native into denatured, you see what it says, that if you convert, let's say this is your denatured, I will talk about this is native, right? If you convert native into denatured, you need to have this energy. You see, when you are converting, if you are converting native to denatured, change is positive. But if you are converting denatured to native, change is negative. When denatured protein becomes native, you come to lower state. But when native becomes denatured, you come to positive state, right? So what I am trying to tell, that from this curve, fraction unfolded curve, at every point you have what fraction native, what fraction denatured, right? Then you can convert this curve like this. And you can extrapolate it to 0, you can know protein is stable. You see, you can, at all concentration you have done it, and you have extrapolated it to 0, you got the stability of a protein in thermodynamic terms. But how this is useful in many studies? Let's see here. What you are able to see? You are comparing two proteins. These two can be just two proteins or two different mutants. We are making changes in protein, you are seeing the effect of mutation. You can tell in quantitative terms that how much energy difference. You can tell that after making mutation, your protein is destabilized by delta G of this. Right? So this type of things you can do using your CD data, where protein before I move on, any questions so far? So what I have explained in terms of application, that you can have a curve where you can normalize your data between 0 to 1, you can plot fraction unfolded, and then accordingly you can have detailed delta G of the protein, you can compare protein, you can compare mutation. I also explained that depending on your fraction unfolded curve, you can identify the protein folding intermediate also, but of course that is not only based on CT, you need to have some supplementary experiments. Right? Now, these are called equilibrium unfolding. Why they are called equilibrium unfolding experiment? And why they are called equilibrium unfolding experiment? Because these are called equilibrium unfolding. Why? Because you are keeping your protein at different concentration of denaturant. You are keeping it for enough time so that native and denatured can get arranged, equilibrated in equilibrium ratio at that particular concentration. And all data is collected in equilibrium state. Right? So this experiment is called equilibrium unfolding. Right? So this is equilibrium unfolding, and based on equilibrium unfolding data, you have derived your thermodynamic parameters. You can derive many more parameters, but I have restricted only for few. But many CDs have study folding kinetics. For example, you have a native protein and you mix it with 6 molar guanidine hydrochloride and you follow the folding pattern or you follow change in signal in microsecond time or even less. Right? So you have a native signal, let's say electricity minus 12. You have mixed it with denaturant, and with time you are seeing how electricity is decreasing. That is called stop flow process. I am not sure it's there or not in this model. It's not there. So you can follow folding kinetics also, right? So I will give you little exposure that for what purpose you do folding kinetics and how we can use it, right? So let's see here. I will just take 10 more minutes. So I hope you have longer class, you start getting bored. What is this slide? What you are getting from this slide? This is energy state of native, this is energy state of denatured. Right? That is what I have explained. When denatured goes to native, energy changes positive. When denatured becomes native, energy changes negative. Now, if native has to go denatured, it must cross a transition state barrier. If denatured becomes native, it also has to cross transition state barrier. What is transition state?
That's a minimum threshold energy required.
Well, I mean, if you have confusion, you can imagine transition state is some intermediate state between native and denatured. This is not correct definition, just to make you understand a little bit, which native must acquire this intermediate state to go into denatured. But this intermediate state is really thermodynamically very unstable, right? And there are some mathematical formulation, Boltzmann distribution, that defines that at any given point how many molecules will cross this. But we are not going into that. What I am trying to explain, unfolding, if native becomes denatured, rate of unfolding depends on this transition state barrier. Rate of refolding depends on this, refolding means denatured to native depends on this transition state barrier. And using three things, stability of native, denatured and transition state means refolding rate, unfolding rate. We can derive lot of it. Let's see. I will come to few examples and then we will have some specific discussion. Let's see. This is what happens. So this is what I have explained. Unfolding depends on this energy barrier, right? And refolding depends on this energy. Right? And this refolding and unfolding can be derived in many ways. I am not going in detail because shop flow setup is not there in this machine. So I am not going in those details. But you can calculate rates of unfolding and unfolding and you can derive many parameters. You can derive that upon making mutations. Is there any change in denatured state? Do you think that denatured state energy can change? Do you think native and denatured state energy is fixed or it can change? How it will change? Native cannot change because native has a one structure. It has a given entropy and enthalpy. But denatured energy state can change. How it can change? No. You see, free energy depends on entropy and enthalpy. Right? What is entropy?
Degree of random is degree of random. Degree of random.
Degree of freedom. Right? Correct? Let's see, I have made a disulfide bond in a protein. I have made two disulfide bonds in protein. What would be the change in entropy of native and denatured? Native entropy will not change because native has just one structure. Right? But denatured entropy will change. Why? Because disulfide bond will restrict freedom in different structure of denatured. Right? So what will happen? If entropy is decreased, then delta G will what would be the effect? You see, decrease in entropy is always uncertain. So delta G, this D will move little up. If D will move little up, then rate of unfolding, rate of refolding will become faster. Right? So, using kinetic analysis, you can have lot of different types of interpretation, you can have lot of different type of information about native, denatured and transition state, right? A typical experiment using kinetic data is called Chevron plot. I have in slide, but because the stop flow is not in the setup, I am skipping that. With this, I am concluding. Thank you very much. You can ask questions if you have. Yeah. You see, I didn't go in those chemistry details. That what I am trying to tell, that right and left-handed absorption depends on also rotation of phi and psi and overall asymmetry of peptide. Structural, right? So it doesn't depend only on transition, but also depends on structural. Sorry?
There is no effect of electronic.
No, there is a, without effect of electronic transition, you will not have it. But it has overall effect of structural. So I will leave this slide if anyone wants to use with a remark that many of these images are not my own. It's taken from maybe some web resources or so. Right? So I will leave it if you want to review. And I think JASCO is also using few of these animations. I have seen on JASCO website. These animations are in JASCO slides. So if you have any more questions, okay.